Hi, I'm Nitish Kumar from ITA. My topic is non-holonomic quantum devices. Abstract, we analyze the possibility and efficiency of non-holonomic control over quantum devices with exponentially large number of Hilbert space dimensions. We show that completely controllable devices of this type can be assembled from elementary units of arbitrary physical nature and can be employed efficiently for universal quantum computations and simulation of quantum field dynamics. As an example, we describe a toy device that can perform Toffoli gate transformations and discrete Fourier transform on 9 qubits. Introduction. What is the difference between a classical and a quantum device? Clearly, it is not in the physical laws governing their dynamics, since classical mechanics follows from quantum mechanics as a limiting case when mechanical action for each degree of freedom is much larger than the Planck constant. Hence, all classical devices are quantum as well, and the basic difference between them is rather in the quantities of interest and in the interactions under control. Typically, the operators of main physical quantities have smooth dependence of their semi-classical matrix elements on the indices enumerating the energy eigenstates, and therefore a state of the device is characterized by the position of the center of the Ehrenfest wave packet in phase space. The average quantities are determined as functions of this position, whereas the finite packet width results in uncontrolled quantum noise and is considered as an obstacle for the correct operation of the classical device in the quantum limit. Non-holonomic control. The idea of controlling a system by forcing it to have globally unconstrained non-holonomic dynamics is natural, since in order to ensure an arbitrary evolution one has first to get rid of the restrictions posed by the existing integrals of motion and all other constraints. In the non-holonomic control scheme, the system evolution is determined by an unperturbed Hamiltonian and a number of perturbations of fixed operator structure and controllable strengths Ci that are applied to the system, so that the evolution is given by the time-dependent Hamiltonian. The system becomes non-holonomic and completely controllable if the commutators of all orders of HO and the PS span the space of Hermitian operators in the Hilbert space of the system. That is, if an arbitrary Hamiltonian operator can be represented as a linear combination of the operators. The control scheme consists of two steps: verification that the perturbations induce non-holonomic dynamics and finding particular time dependencies for the perturbations that affect a given desired control. Step 1 is straightforward by inspecting the cumulation relations between the explicitly written Hamiltonian and perturbation operators, and once checks if the system under consideration is instead non-holonomic. But step 2 requires more art. One has to put the system in such conditions that all unwanted outcomes present in abundance in a system with no constraints experience a destructive quantum interference. Let us consider a quantum system of n equal to 2n levels composed of n interacting two-level subsystems. To be specific, we speak about two-level atoms in a laser field, although it could as well be any other quantum object such as interacting spins in a magnetic field, Josephson junctions, Rydberg atoms, rotating molecules, quantum dots on a surface, etc. The only requirement is that the object must be subjected to a non-holonomic control, since only in this case you can perform any desired operation no matter what the physical interactions in the system are. The choice of a practical realization of a non-holonomic system will therefore depend mainly on optimization of technique parameters such as simplicity and cost effectiveness of construction, lifetime of quantum coherence, precision of available controls, and so on. A crucial issue that determines the strategy of construction is the required extent of immediate universality of the control. In principle, one can think about complete direct physical control over a 2n level quantum system, even for a large n, which implies the ability to ensure an arbitrary evolution of the system given by an predetermined 2n unitary matrix and which requires foreign physical control parameters. For this purpose, one should find an algorithm that determines these controls for any given U. It might be difficult to find such algorithm, and even if found, its applications will require an enormous computational work that grows exponentially with n and will therefore be interactable. In addition, the cost of physically implementing the huge number of foreign control parameters seems too high a price to pay for this kind of universality, which may not even be needed for practical purposes. For these reasons, one should premisely give up direct universality and search for specialized ways to build quantum devices for each particular task with number of controls that is not exponentially larger than what is specially needed. Complex control unit cell. One way to construct a completely controlled but not immediately universal quantum device is build it up from small parts, unit cells, each of which is non-holonomic and therefore directly and universally controllable. The proper functioning of the device release then and the appropriate connection of the calls. The universality of the device is obtained indirectly not by applying a huge number of controls, but by smartly connecting the cells and choosing the sequence of operations performed. There is no general prescription how to construct a particular device. This requires expertise in the art of programming, the operations of the cells and their interactions. Conclusion. We have shown that quantum devices with exponentially large Hilbert space dimension can be efficiently controlled, provided they are assembled from completely controllable unit cells in an architecture that is optimized for the special function they should perform. The unit cell can be constructed from simple quantum objects of arbitrary physical nature, two-level atoms, nuclear spins, rotating molecules, quantum dots, etc. Cells to optimize critical properties such as coherence, time, and control precision for practical realizations. The only requirement is that the unit cell could be put under non-holonomic control, that it could be sufficiently perturbed to have unconstrained dynamics. This ensures that the cell can be fully controlled and made perform any desired operation. As a concrete example, we have considered a quantum system of two n levels composed of n two-level atoms that are coupled by dipole-dipole interactions. The atoms are grouped into unit cells, each consisting of three nearly resonant atoms. Each cell is controlled with two time-dependent perturbations, a static electric field and an electromagnetic field nearly resonant with the atoms. We have shown that an unitary transformation in the 2-3 equals to a dimensional Hilbert space of the cell can be effected within a few control cycles, each comprising 64 applications of the perturbations with values fixed according to the non-holonomic control scheme. In particular, the Toffoli gate transformation on the cell recorded as a 3-qubit register and any permutation of the three. Thank you. This is my presentation.